Climate reconstruction using dendrochronology as climate proxies. Hi everyone, my name is Byron Arana. Today I'll be presenting on tree ring chronologies to understand how climate has changed over time. For the peer-reviewed tree ring studies, I chose to focus on two regions, the Colorado River Basin in North America and the Pueblo region of the southwestern United States. Tree ring data offers crucial insight into long-term climate patterns, which are essential for understanding both past and future climate change. So where does the data come from? Tree ring data comes from analyzing the growth rings of trees, which reflect annual growth influenced by environmental factors like temperature and precipitation, as explained by Antiochitis. Instrumental records are limited in length and geographic coverage and too often can't reconstruct past climates beyond a few hundred years. Tree ring data comes from the International Tree Ring Bank known as ITRDB, mainly the Northern Hemisphere mid-latitudes. The Southern Hemisphere creates limitations due to trees not producing annual rings. Despite these limitations, tree ring research has been ongoing for over a century, providing critical information into climate history. The most common measurement is the width of the annual ring, which reflects the annual growth and annual growth patterns. It can be influenced by factors like temperature, rainfall, and soil conditions. The rings can be dated to their year of formation, which allows scientists to precisely date past climate events. Wood density, especially near the end of growing seasons, reflects summer temperatures. The oxygen isotope composition of the wood can reveal information about the water source, the extent of evaporation in the ecosystem, and seasonal rainfall variations. The image on the right illustrates how tree rings can show differences between wet and dry seasons, which is crucial for understanding past climate fluctuations. The first location located in the Ferrel Cell is the Colorado River. The graph on the right compares observed data, blue line, with tree ring reconstructions, black line, from 1900 to 2008 CE. Data alignment shows that tree ring reconstructions correlate with observed data. According to Antiochitis, the close alignment between the two shows that tree ring data can reliably reflect past river flows. Tree ring reconstructions of past river flow indicate that the Colorado River has been overallocated in terms of water supply, even without human interference. These extreme periods of reduced flow are possible, which would be crucial for managing water resources in the future, especially given the impact of climate change. Using tree rings, we can reconstruct a graph dating back to 760 CE. It reveals that the early 20th century was unusually wet, contrasting with much drier periods in earlier centuries. For instance, from 1143 to 1155 CE, there was a 13-year period of significantly reduced flow in the river. The observable flows only provide a short-term or snapshot of the overall river flow. Tree ring records provide a more complete picture of past conditions. These long-term reconstructions are a more accurate representation that can be used in simulations to help water management personnel understand the potential future impacts of water shortages because of climate change. In the study, scientists found through simulations that the Colorado River Basin aggravates future water shortages, but both the timing and severity of water shortfall depend on baseline conditions. Furthermore, Antiochitis, Miko, Woodhouse, and Marino used a river management model to demonstrate that a period of Colorado River low flow similar to that reconstructed for 1143 to 1155 CE occurred today. It would lower Lake Mead to below its outlet of Hoover Dam within a few decades. Our second location, located in the Ferrel Cell, is the Pueblo region. In this graph, tree ring data from the late 12th and late 13th century reveals the extent of severe droughts or megadroughts that affected North America. The reconstructions examine soil moisture, as tree growth is more strongly linked to soil moisture than rainfall alone, which suffered during these droughts as explained by Antiochitis. This is crucial for understanding agricultural impacts of the past. For example, the second graph dated 1276 to 1297 CE demonstrates a two-decade drought in the late 13th century, coincided with the collapse of and migration of the ancestral Pueblos peoples in the southwestern U.S. The 1130 to 1155 CE graph includes the 12th century drought, which corresponds to a decade of reduced river flow in the Colorado River Basin, as shown in the river flow graph on slide 5, and is linked to decreased soil moisture. These graphs help climatologists understand the past climatic extremes, which can inform how current and future droughts might impact ecosystems and societies. The 1130 to 1155 CE graph includes the 12th century drought associated with a decade of reduced river flow in the Colorado River Basin. This graph illustrates one of the most extreme droughts in the region's history. By studying these reconstructions, as explained by Antiochitis, climatologists gain a deeper understanding of past climatic extremes, which helps inform current water management strategies and prepares us for potential future water shortages. This graph shows Northern Hemisphere temperature data from 1400 to the present, based on tree ring data from the famous hockey stick study by Mann, Bradley, and Hughes, and further developed by Andrikaitis. The red line being the 1998 extended Northern Hemisphere reconstruction shows a long-term cooling trend from the medieval period until the late 19th century, followed by a sharp warming trend in the 20th century, often called the blade of the hockey stick. This rapid warming is linked to human-driven climate change, highlighting the significant role tree rings play in distinguishing natural climate variability from anthropogenic influences. In conclusion, tree ring data is an invaluable tool for understanding both past and present climate conditions. By looking at these long-term records, we gain insights into natural climate variability, and trees will continue to reflect the changing climate.